My name is Sudeep Shekhar, and I'm the chair for this session. I'm from University of British Columbia, it's in Vancouver, and my co-chair is Professor Shreyas Sain. He's a professor at Purdue University. And our first speaker is Dr. Ganesh Balamurugan. Ganesh received his B.Tech degree from the Indian Institute of Technology, Madras, in 1996. And his master's is actually from University of Texas, Austin, in 1998. So welcome back, Ganesh. He got his PhD degree from the University of Illinois, Urbana-Champaign in 2004. And since 2004, he has been with Intel working on I/O link modeling, SerDes design, and optical transceivers. So Ganesh is famous inside Intel for developing a lot of link modeling and link simulation methodology and even tools that's used widely across Intel for link modeling and design. He's currently a principal engineer at Intel Labs. So without further ado, let's welcome Ganesh.
Okay. Great, thanks for the introduction. I'm happy to be here and talk about standards, link models, and link budgets as they relate to links that are 50 gigabits per second or higher. And before starting, I want to acknowledge the help from my co-authors at Intel, Ajay and Chunming, who helped to pull this presentation together. So here's a brief outline of my talk. First, we'll start with some background material that shows wireline trends, the drivers for those scaling trends, and also look at an example that gives a short preview of all the subsequent material and also helps kind of set some context to it. Then I'll talk about the standards themselves, the 56 gig standards, which are mostly finalized, most of them are finalized, and the 112 gig standards, which are currently under development. And we'll talk about both the electrical link side and the optical links. And then we'll move on to link budgeting. So the standards specify what kind of SNR budget you want your link to achieve, and it's up to the system designer to figure out, okay, how do I divide this available SNR budget between different link impairments. So we'll talk about that in the link budgeting section. Then finally, we'll look at link models, what they enable, and some examples showing how you can use these models to do SerDes design. Okay, so let's start with the introduction. So here, like I mentioned, there will be two parts. The first one will just go over the trends, wireline trends, to give some background and motivation. And then the second part, we'll look at an example, 400 gig data center link, and how standards, budgets, and models relate to this. So this chart, you may have seen this before, shows how wireline data rates have been increasing at a steady clip over the past more than a decade or so. So they've roughly doubled every 3 to 4 years, give or take, and more recently they've actually accelerated a little bit. From 28 to 56. Now 112, there are a lot of exploratory work happening beyond 112 and 224 gigabits per second. So there's no sort of immediate signals that the scaling trend is slowing down. So 28 gigabits per second solutions have obviously been deployed. A lot of 56 gig solutions are being deployed. Currently, we saw quite a few 56 gig SerDes papers in 7 nanometer at IEEE a couple of years back. There were quite a few demos of 112 gig SerDes at OFC, the Optical Fiber Communications Conference last month. So there's a lot of interesting work, and like I mentioned, people are looking beyond this also actively. So what's driving the scaling trend? It's primarily driven by two things: the internet traffic, which is all the data generated by our smart devices, and a lot of the computing moving to the cloud, and that's also driving the need for high performance, high bandwidth interconnects. And there's the upcoming transition to a new wireless technology, 5G, which is going to increase the data rate and the number of nodes. So we can expect an acceleration in this trend and a greater need for high bandwidth interconnects. So the brunt of this bandwidth demand is obviously felt in the data centers, where the data is stored, processed, moved around, and generally sort of made sense of. So they've been obviously evolving to meet this bandwidth demand. So there's an interesting paper, sort of a retrospective paper from Google a few years back that talked about how the Google data centers have evolved to meet this huge increase in network bandwidth. So this is the traffic within the data center itself over a relatively short period of time. So they've looked at the bandwidth they had to support from the beginning of life of the data center to, over a decade, and found that there's actually a 100x increase in bandwidth that happened over that time span. And obviously there are many elements to the solution, but from a hardware standpoint, the two key things that are required to sort of sustain or enable the scaling were the switch silicon and the electrical and optical interconnects, which is kind of the focus of this discussion here. So there's a variety of interconnects that are being used in data centers currently, starting from electrical interconnects. So this is for communicating between the servers in a rack. So that's starting to transition from sort of traditional FR4 backplanes to more cabled backplane solutions. Going to thicker and thicker gauge cables to support the 2 to 3 meter reach that is required in the backplane. And beyond that, from like 3 meters to about 100 meters or so, we are seeing the use of parallel multi-mode fibers. So these are typically VCSEL-based, and we'll probably hear more about this in the following talk by Professor Jitter. And then for longer distances, from 100 meters to 2 kilometers or even 10 kilometers, people are turning to single-mode fibers. And these are increasingly silicon photonic-based solutions. So clearly, there's a sort of variety of interconnects that need to be supported, and that's why we need sort of both electrical and optical links to enable the final end-to-end link bandwidths that we need. So the standards and ASICs have also evolved to sort of meet this increasing bandwidth need. So if you looked at 2016 and before 2016, most of the solutions were 28 gig ASIC based, and typically in 28 nanometer or below. And so now we are seeing that moving to more advanced process nodes and at 50 gigabaud and 28 gigabaud PAM4 and 50 gigabaud PAM4 in the very near future. So what I've indicated in the box here, that's what we are going to be talking about, the standards and the models for as they relate to sort of this space, 56 gig and 112 gig optical and electrical links. So in order to give some context to sort of all the subsequent discussion on standards and budgets and models and so forth, I thought it'd be useful to just walk through a typical data center link example and then kind of attach these concepts to that. So it makes the subsequent discussion a little more concrete. So let's look at a link that's used in the data center to attach between two switch units. So what's shown on the left and the right are rack units in a switch chassis. And we want to communicate from one switch IC to another switch IC. And these, with sort of the sprawling data centers we have today, the link can span several hundred meters. So clearly we need sort of single mode optical fiber to span most of that reach. And the plugin, the optical plugin to the rack itself is through these pluggable optical modules that plug into the faceplate in the rack unit. And the optical transceivers themselves are housed within these modules, and they communicate with the switch IC through an electrical link on the PCB. So this is how an example, like 400 gig data center link, a long reach short reach from an optical sense, but a long reach from an electrical sense data center link would look like. So it's more clear to see what the components of the link are in this schematic view, where we have the switch IC on a package communicating with the optical transceiver through a few inches of baud trays, both on the PCB and in the module. And then the optical transceiver itself, which typically includes the retimer and the optical interface circuits sitting in the module housing, and then it communicates through single mode fiber to the corresponding circuits on the other side. So the key thing to note here is there are actually two distinct links. One is a relatively short electrical link from the switch IC to the module, and the other one is a longer link, longer optical link through single mode fiber. So what are the standards that are relevant in this kind of link scenario? So for the short electrical link, those would, to support 400 gig bandwidth, there are multiple choices. We may want to use like 4 lanes of 100 gig each or 8 lanes of 50 gig each. And depending on the choice, we would choose to design 2 different standards. So for example, in this, here I'm showing that we have 4 lanes of 100 gig each. So this is anticipating that CEI 112 gig VSR would be standardized soon. And in that case, we would design the SerDes both on the host side and the line side to conform to the CEI 112 gig VSR, or very short reach link. So in the subsequent slides, we look sort of in more detail about what these standards entail, but here I just want to introduce sort of the terminology and like what standards relate to which portions of the link. And for the optical side, for the single mode fiber, here if you're using 4 parallel fibers to achieve the 400 gig aggregate bandwidth, then we would target a standard like 400 gig DR4, which dictates what kind of specs we need to meet at the 2 ends of the fiber for the optical transmitter and the optical receiver. So these standards kind of specify high-level specifications like what kind of baud rate to use, what modulation scheme to use, and what kind of end-to-end target bit rate we need to achieve. So now we need to take those and convert it or divide it between different link impairments. So on the electrical side, we would have insertion loss, crosstalk, and so forth. And the system designer needs to figure out, okay, how do I budget this available SNR between all these impairments? For example, less than 10 dB for insertion loss, less than 2 millivolts for integrated crosstalk noise, and so forth. So that's the link budgeting exercise that we'll talk about later. And similarly, on the optical side, we need to divide the available SNR budget between how much loss can you tolerate on the modulator, the optical modulator itself, how much loss can you tolerate in the link, what kind of receiver sensitivity do you need, and so forth. So that's what link budgeting entails. And so finally, the link models, which are basically abstractions of the physical link itself, what they enable to do, and which is probably of most interest to circuit designers, is convert all these specifications into actual circuits. So we can, from the models, we can figure out, okay, how do I divide the equalization burden between the host side SerDes, the line side SerDes, what kind of CDR to use, what kind of resolution do I need on the ADC, DSP, and so forth. And similarly, in the optical side, we can use the models to figure out what kind of bandwidth and linearity specs do I need to meet on the modulator side, what kind of PDs or photodiodes or TIAs do I need to design, and so forth. And so they enable to convert sort of these higher level specifications from standards and budgets into lower level circuit building block specifications. And of course, they also help to validate sort of final end-to-end link performance. So that's just kind of a short preview of the following material, and hopefully give some context to the subsequent discussions. Okay, so next we look at the standards themselves. I'll start with some background which gives an overview of all the existing standards out there and the ones that are currently under development. Then we look at the electrical standards in more detail. I'll pick the CEI 56 gig LR standard in order to sort of highlight some of the specs that are relevant to circuit design and that have some impact on the circuits themselves. And then we look at a similar example on the optical side, the 400 gig DR4 standard. So both these standards have been finalized within the last year and a half or so. Okay, so before we sort of dive into the standards themselves, it's sort of useful to remind ourselves why they exist in the first place. So standards at sort of very high level, they enable multiple vendors to design components to a common set of specifications and have a high degree of confidence that they can work well together. So broadly, they allow, by allowing multiple players, they help to reduce cost, build scale, and then have the benefits of that scale sort of distributed over a wider set of players. And so one important thing to note is that there are some pretty strict criteria for standards development, and besides technical feasibility, which sort of the so-called hero experiments demonstrate, there also needs to be a strong economic justification for standards development. And at least for the last couple of generations, that hasn't been hard to make, given all the trends we've seen so far. But yeah, that's those things that are useful to keep in mind. On the wireline side, the two key standards bodies have been the Optical Internetworking Forum, or OIF, that typically has taken the lead in developing the electrical interface standards. So these are the so-called CEI, or Common Electrical Interface specs. And then on the optical side, the IEEE 802.3 body has been sort of the leading standards organization for a few decades now. So this is the Ethernet working group. And the timeline here kind of gives you an idea of how the standards evolve, at what kind of pace. And it's over the last couple of generations, at least, we have seen sort of a new standard take anywhere from 2 to 3 years of completion. So the CEI 4.0 standard, which was approved at the end of 2017, that's the 56 gig link standards. So the 112 gig standards are sort of actively under development, and we expect we'll see a sort of final draft probably by the end of this year or early next year. Okay. So here I'm just showing a partial list of sort of all the standards that are out there on the electrical side and the optical side. Again, I wouldn't pay too much attention to sort of all the actual specific or the actual designations. We'll look at it in more detail in a subsequent slide. But the point here is just to show that there is actually a wide variety of standards that span the several different reach and media requirements, both on the electrical side, like the way of CA standards, and on the optical side, the Ethernet standards. So before looking at the standards themselves, what I just want to summarize sort of what the key challenges or the key changes were in 50 gig and beyond versus what we saw before at 25 to 28 gig speeds. So probably the biggest and the most important one has been the transition from binary or NRC signaling to 4-level PAM4 modulation. So the transition that people have anticipated for a really long time has finally happened, and almost 90% of the links that are being designed for 50 gig and above are using PAM4. There are a couple of exceptions that I'll point out later, but for all practical purposes, I mean, all the links, both on the electrical side and the optical side, have transitioned to PAM4 signaling. And this has come with a few significant changes. The first one is the significant relaxation in the uncoded raw or pre-FEC bit error rate. So it used to be that people were targeting 10 power minus 12 or better bit error rates before. But now the specs dictate bit error rate targets significantly smaller, 1e minus 4 to 1e minus 6, depending on the reach. So there's, although the standards don't dictate what type of FEC needs to be used, there's an implicit assumption that FEC will be used to improve the bit error rate from 1e minus 4 or so to 1e minus 15. So that FEC overhead needs to be budgeted for upfront. Obviously, with the multi-level signaling, there are also new linearity metrics like ratio level mismatch and TDECQ that we'll talk about in more detail subsequently. And this obviously has some design implications too. It places new constraints on both your transmitter and receiver circuits in order to maintain linearity in your signal chain. And finally, the standards are also now explicitly accommodating ADC and DSP-based transceivers, or they made changes to accommodate these transceivers, whereas previously they were largely agnostic of the actual implementation. So I suspect we'll hear more about this in the third talk in this session by Dr. Franz. So I'll just mention that in the context of standards, what that's translated to is a reduction in the jitter tolerance corner frequency. Again, this is something we'll see later. So the point is there are quite a few significant changes in going to 50 gigabits per second and beyond from sort of previous generation SerDes and link designs. So here I'm showing a summary of all the CEI, or Common Electrical Interface standards. So again, like I mentioned before, these are the standards that OIF develops, and then they're adopted with little or no change by the IEEE Ethernet group. So the standards themselves, they span a fairly wide range. So on the low end of the reach, we have the CEI 56 gig USR, or ultra short reach links. So this is intended for very short links between, say, two dies on a package or on a stack. And going to XSR, or extra short reach, which is just slightly wider separation, but still no connectors, to very short reach, or VSR, example being the chip to module. So this is the same example that we saw earlier, where the switch IC was communicating to a transceiver in a pluggable module. So this is a fairly common sort of spec to design for. And then a medium reach, or MR, and then finally the LR, or long reach, which targets the backplane, or increasingly a passive backplane, a passive cable channel. So you can see that the loss targets are at the high end, which is typically what people design for, and obviously the most challenging one to design for. People target designing for something in the 35 to 40 dB loss range. And if you notice the loss specifications here for 56 gig PAM4, 56 gig aggregate data rate, VSR and above, the loss specs are at 14 gigahertz, so that's an indication that it's PAM4 modulation. And then USR and XSR are actually spec'd at 28 gigahertz, so that's NRZ modulation. So those are the two exceptions that I mentioned earlier to PAM4 modulation, where for these really short reach links, you don't want to incur the latency and power overhead of FEC, and it's actually possible to close the link budget without that. And so those are the only two cases where NRZ's implementations exist. Everything beyond that has transitioned to PAM4. So this is sort of a summary table from the Ethernet Alliance showing all the Ethernet standards that have been developed since the dawn of Ethernet, 10 megabits per second, to where we are today, which is 400 gigabits per second. So each row corresponds to one target aggregate bandwidth, and each column is a different physical medium. So starting with electrical interfaces all the way to 80 kilometers single mode fiber. So the ones that we are interested in are sitting at the bottom of this table. So these are the links that are targeting 50 gigabits per second per lane or above. And here, there's a more detailed decoder for this in the next slide, but I'll just point out here the ones that we're interested in are the ones highlighted here, where actually there's one, the 50 gig AUI is also a 50 gig link. But there are quite a few standards that have been recently developed or ratified for 50 gig and beyond electrical interfaces and optical interfaces. So, if you are not familiar with Ethernet terminology, it can be a little intimidating to decode the standards nomenclature, but it's actually fairly simple. So the first designator is the aggregate bandwidth that the link is targeting, and then there are some designators that designate the medium and the number of channels. So, for example, 400 gig based DR4 would use 4 channels of single mode fiber. The D refers to 500 meter single mode fiber, and because 400 gig is aggregate data rate, each lane needs to support 100 gigabits per second. And similarly, the other common ones are 100 gig KR4 or 100 gig KR or 100 gig KR2, things like that. And typically, the electrical interfaces, like the chip to module interface that we saw before, they have slightly different terminology depending on whether you're looking at coming from the Ethernet side or OIF CEI. And there's actually almost a one-to-one correspondence between the two specs. Typically, the CEI specs are developed earlier, and then they're adopted by Ethernet, but the name of the standard has changed. So here are a couple of correspondences to help decode or translate one to the other. So 400 gig AUI 8 chip to module spec would be, for all practical purposes, identical to the CEI 56 gig VSR spec. So for the subsequent discussions, for the electrical specifications, I'll stick with the CEI spec terminology, and then for optical, I'll use the Ethernet terminology. So let's take a closer look at the electrical standards themselves, and again, some of the key specifications that as circuit designers we need to be aware of while designing these SerDes links. So rather than looking at the whole span of specification that I showed earlier, I'll focus on the CEI 56 gig LR spec. I mean, this is typically the most challenging spec since it's targeting the longest reach for electrical links. And then to point out differences from the other specs as they're relevant. So here, the target baud rate is 28 gigabaud PAM4 to meet the 56 gig aggregate data rate. And the bit rate spec is 1E-4, the raw bit rate spec. And there's some differences in this target bit rate spec depending on the reach of the channels. For example, CEI 56 gig VSR allows or has a more stringent target of 1E-6. And like I mentioned, the XSR and the USR, the very short reach, I mean, they have the 1E-12 bit rate target because they don't assume effect at all. But for all purposes, we are focusing on LR, and so the bit rate target is 1E-4, with the assumption that the forward error correction will get us from here to 1E-15. So here's an channel spec guidance to help design the channel for this the specification. The insertion loss targets are from just a channel standpoint, so this is from the package ball on the TX side to the package ball on the RX side. We want to achieve less than 28 dB at Nyquist, which is 14 gigahertz for 56 gig PAM4. But it's important to note that the packages themselves on both the TX and the RX can actually add significant loss. So 3 to 5 dB is pretty common. So if you look at the SerDes themselves that are designed for this kind of standard, they'll typically target the 35 to 40 dB insertion loss. So it's important to add this package loss overhead when looking at the channel specs in the standards document. And it's also important to note that the standards have kind of gone away from the channel mask specifications like this. So this more for it's what's called an informative spec. So it's not necessary that the channel actually meet this spec. The more so the required spec is specified in terms of this parameter called the channel operating margin that we'll again talk about in the link budgeting section. But this gives some idea of roughly what kind of loss targets you want to design for. So that was the channel. So on the transmitter side, there are specifications on the levels themselves. Like I mentioned, a new specification, because we are transitioning to PAM4, is this ratio level mismatch, or RLM spec. It essentially captures the level asymmetry in a sort of average or DC sense, and how much they deviate from ideal levels. So an RLM of 1 means that you have ideal PAM4 outputs, and anything below that means there is some deviation from that. So typically, people design for, or are required to design for RLM better than 0.95. The picture here, that's from a very good tutorial on PAM4 signaling in DesignCon, shows what, that's in the reference list, that shows what the impact of deviating or from this RLM spec or PAM4I asymmetry is on bit error rate. So you can see that small deviations can actually have significant impact on the overall link bit error rate. So it's an important spec to design for. And typical transmitters actually have hooks to pre-distort these levels in order to undo any kind of level distortion that subsequent circuits introduce. Another spec that is intended to constrain this the amount of nonlinearity and distortion that can be introduced in the signal chain on the transmit side is the signal to noise and distortion ratio, or SNDR spec. So the way it's defined is it's defined as the ratio of the signal content in your transmitter output to the systematic noise or distortion or systematic distortion that's introduced in the signal. Or systematic deviation that's introduced in the transmitter output from what you would have gotten with an ideal linear transmitter, and also the additional random noise that's added. And so it's important to note that it discounts ISI, or the limited bandwidth of the channel. So an ideal, if a channel was linear, or if your transmitter was perfectly linear but had limited bandwidth and introduced no noise, you would have infinite SNDR. So any deviation or any reduction or change from that is an indication of how much distortion and noise, for example, from your termination resistors, your output devices, and the distortion could come from the limited resolution in your DAC, any kind of compression you're seeing, and so forth. So the picture here is an example that was presented at IEEE last year, one of the 56 gig LR SerDes designs. It shows the kind of RLM and SNDR they've been able to achieve in their 7 nanometer design. So it's significantly better than what the specs require. And it's usually required in order to close the budget in these high loss channel scenarios. The other important transmitter specification is the jitter. So to some extent, the jitter spec has been simplified from the past generations. So now there are just 3 components of jitter: the RMS jitter, what's called J4U, and then the even odd jitter, which is actually just unicycle distortion. So the J4U jitter is essentially just the span of the jitter in your sort of output jitter PDF that includes all but 1%, all but 0.01% of your overall jitter. So there's a 10 power minus 4 probability, which is also the target bit error rate, that your jitter falls outside the span. And there's a pretty systematic way that the standards define in order to compute this, in order to get rid of effects like correlation or ISI-induced jitter and so forth. And JRMS is nothing but the standard deviation of this jitter. So to look at some actual numbers for 56 gig, the J4U, you don't want it to be more than 12% of your UI. And the RMS jitter itself, translated to picoseconds, is less than 2 picoseconds of RMS jitter. And they'll scale roughly by a factor of 2, going to 112 gig. And we'll talk a little bit more about how one can go about analyzing the jitter contributions of different circuits in the clock path and what you can do to optimize it in the link modeling section. The return loss is another important spec, which is usually non-trivial to meet on the transmit side. The intent here, the intent for including this in the standard is obviously to limit the impedance discontinuity of the TX, but the reason that is important is usually there are significant reflections at the package interface, and if they are not absorbed by the TX side, they'll bounce back to the receiver and cause reflection-induced ISI, which is actually much more detrimental for PAM4 than for NRZ. So it's important to control that, and the spec dictates better than 6 dB return loss below Nyquist. And typically this will require some kind of distribution of your pad parasitics, like what is shown here from a 112 gig TX design. So you'll want to split your driver parasitics, the termination parasitics, and potentially even the ESD will need to be distributed in order to achieve this return loss spec. And a side benefit of doing this is also some bandwidth extension that you can pick up. Moving to the receiver side, the specifications are comparatively simpler on the receive side. Essentially, the tests, the standards specify some tests that need to be run in order to make sure that the receiver works with a combination of worst case channel and worst case but compliant transmitter. So for example, if your transmitter has the RLM limit, so introduce some distortion, so its RLM is 0.95 and the jitter specs, and you have the worst case channel, your receiver should still meet the target bit rate, in this case of 1E-4. The jitter tolerance test, while the mask looks similar to before, there's a corner frequency and then the floor is around 0.05 UI. The key change has been the location of that corner frequency. So below the corner frequency, the receiver is expected to track and reject the transmit jitter. But that corner frequency used to be 10 megahertz in almost all the previous specs. That's been pushed down to 4 megahertz, 450 gig and beyond. And this is primarily to accommodate the additional latency in the CDR path that you incur with an ADC and a DSP-based transceiver. So again, I think we'll probably hear more about this in a subsequent talk. So the important thing to note here is that there has been a significant change in the corner frequency. The implication being now that on the transmit side, there are more stringent constraints on how much jitter can be in the frequencies beyond 4 megahertz. So you need to pay more careful attention to the design of your transmit PLL and the clock distribution. Okay, so now let's switch gears a little bit and talk about the optical standards. So the table here summarizes the standards that have been recently ratified and are also in the process of active development for 50 gig and beyond, spanning 100 meter SR short reach, which is the VCSEL-based multi-mode fiber type channels, and then 500 meter and above is single mode fiber, like I talked about before. The categorization here, similar to the XSR VSR categorization on the electrical side, is 500 meter is DR, 2 kilometer is FR far reach, and then 10 kilometers long reach. And there's actually also standards being developed for 80 kilometers, so inter or intra-data, long intra-data center links using coherent optics that are not listed here. So for our purposes, we'll focus on everything 10 kilometers and below, because to a large extent, we can neglect the effects of fiber dispersion in that regime. So for the following material, I'll pick the 400 gig DR4 standard as a reference. So this is essentially four channels of 4 parallel channels of single mode fiber with 100 gig bandwidth per channel. for an aggregate 400 gig bandwidth. And here, again, like I mentioned, the transition to PAM4 has happened on the optical side as well. The target bit rate is slightly different, but of the same order as CEI 56 gig LR. So it's a little over 2 E-4 prefec. So again, the assumption is that we'll have appropriate FEC to improve the overall bit rate or the end-to-end bit rate to 10 power minus 15. Okay, so if we look at the transmit side, the specifications, the signaling rate, it's in the 50 to 56 gigabaud range. The actual rate is essentially includes the expected FEC overhead and like 6466 coding overhead and so forth. So that's why it's this odd number between 50 and 56. The key specs to look at on the transmit side are specifications of the levels, so the optical modulation amplitude and the extinction ratio, which will be defined in the next slide. And the big change here versus previous specs has been the introduction of this parameter called TDECQ, which again we'll look at it later, look at the actual definition later, but it's intended to capture all transmitted non-idealities into one number, the nonlinearity, the limited bandwidth, and so forth. So the difference from the previous spec has been that previously there have been these masks that have been specified for the transmitter output to meet, and that's essentially gone away because it's, it was found that it was pretty much useless for these data rates with PAM4. You have to try to meet mask without any post-processing of the TX output. So I'll talk about what kind of post-processing and reference receiver needs to be applied to the TX output in order to extract these parameters later. So the optical modulation amplitude and extinction ratio are defined in this slide. So if you, from the PAM4 for optical output, we can extract the 4 DC levels. The optical modulation amplitude is nothing but the difference between the highest and the lowest averages. And it's called outer optical modulation amplitude because in the PAM4 context, these are the outer levels. And similarly, the outer extinction ratio is simply the ratio of the highest level to the lowest level. And both of them are usually expressed in dB. The two can be set independently, but from the two, you can derive what the average output power is using a simple expression. And the reason they are spec'd separately is to limit the amount of average power out of the transmitter, both from a power standpoint and also from a receiver power handling standpoint. So if you had infinite extinction ratio, your average power would simply be half of your OMA. And for any finite extinction ratio, the average power keeps inching up, and so you want to place a cap on that in order to limit that average output power. So here's some more details about the much talked about TDECQ metric. TDECQ itself stands for transmitter and dispersion eye closure quaternary. The terminology just evolved from what used to be called a TDP spec, a transmitter and dispersion penalty spec for NRZ, and in the process of trying to modify it to PAM4, the label also got bigger. There's been a lot of discussion on how the spec needs to be defined in order to achieve sort of close correlation with your receiver sensitivity. So the problem here is you want to come up with a transmitter spec that can be consistently measured with independent of what kind of optical receiver you're using for measurement. So you should ideally get the same number for a given transmitter, regardless of what instrumentation you're using for measurement. And it took a lot of debate and discussion to actually settle on what that should be. But now that's been finalized, and people have actually shown through measurements that with different transmitters and receivers that there is good correlation between this metric and what we ultimately care about, which is the receiver sensitivity. So what is TDECQ? The idea is actually fairly simple, even though the measurement process is kind of complicated. All it is saying is how much is the SNR of your actual transmitter degraded versus an ideal or predefined ideal transmitter for a given reference receiver. So that's more or less so in other words, how much less noise can your actual transmitter tolerate versus an ideal transmitter for the same receiver. So the definition and the measurement methodology is more involved and sort of detailed in the spec document, and most of this is actually handled by the test instrument. It's important to understand the method just to interpret the test results. And effectively, I mean, it involves finding out where your sampling point needs to be, and because the reference receiver itself is a combination of this fourth order Bessel-Thomson filter with baud rate, with half the baud rate bandwidth, and a 5-tap symbol-spaced FFE, there's an iterative process involved in figuring out what is the optimal receiver in order to get your best TDECQ. So most of the complication comes from being able to figure out what these receiver coefficients need to be to balance the noise amplification that's introduced by that receiver versus the ISI reduction that the receiver enables. But I mean, most of that happens sort of behind the scenes, but it's important to understand that that is happening. And then with that reference receiver, you want to figure out, okay, what's the best transmitter I or transmitter SNR that I can get. And then compare that against what you would have gotten for sort of a more ideal transmitter without distortion and noise. So to put some, it's actually easier to see this in actual pictures. So here I'm showing two measurements that we did recently on a 112 gig optical transmitter. So there's a silicon photonic ring modulator based transmitter that we presented at OFC last month. So the plot on the left shows what the optical transmitter output looks like so to step back, the microring modulator itself is nonlinear. I mean, its bandwidth varies as a function of your output swing. And so you need some kind of compensation circuitry on your driver in order to compensate for that. So the plot on the left shows what the output looks like with that compensation enabled. The plot on the right shows the output with that compensation disabled. And then I'm also showing what kind of TDECQ we measured using an external sampling scope for the two cases. So you can see that the TDECQ value is higher on the right, where your eyes are kind of skewed with respect to each other, which is a classic signature of optical modulator nonlinearity. And because now your levels or your eye opening is smaller at your nominal sampling point, that's reflected as a higher TDECQ value. So roughly what this means is with no nonlinearity compensation, you can expect to burn 1.5 dB more optical power, or require a receiver that is better sensitivity by 1.5 dB or so. Okay, so moving to the receiver side, here the key numbers are the receiver sensitivities, of course. So the average, if you look at the average power range, this is saying that the receiver needs to tolerate at least 10x or 10 dB range in dynamic power. And so typically there is some gain adjustment circuitry, and your DC offset compensation circuitry needs to accommodate that. The required receiver sensitivity spec is what's called the stress receiver sensitivity, where you apply these external stressors to mimic your worst case transmitter and channel conditions, and you want to achieve your target bit rate with -2 dBm input power or lower. So to get an idea of what the test setup looks like for this test, so this is very similar to the interference tolerance test that you do on the electrical link side, with some subtle changes. So the idea is you add this these stressors on your transmit side. I mean, primarily a low-pass filter in order to mimic transmitter bandwidth limitation, additional noise sources, and then calibrate your transmit signal in order to make sure that they meet your worst-case transmitter specs, and then add sinusoidal jitter in your transmit clock source, measure your receiver beta rate, and see if your receiver meets this JTOL spec mask, which actually is identical to the mask on the electrical side, and that's no coincidence because usually you want to reuse the electrical SerDes for all your optical transceivers as well. So in this slide, I'm just listing some numbers that's useful to keep in mind when looking at optical channels or budgeting optical channels. The spec itself allows 3 dB of insertion loss budget for the end-to-end link. And the fiber loss is typically well below 0.5 dB per kilometer. So this implies that for 500 meters, is 0.5 kilometers. For DR4, we have about 2.75 dB allocated for all the connectors and splices. So typically this allows for 3 or more connections. And fiber dispersion is usually negligible for definitely for 2 kilometers and less at these data rates. Partly because we're signaling at 1310 nanometer, which is the zero dispersion point for the fiber, and partly because we are not, in optical sense, we are not signaling over extremely long distances. This is a little different for example, the 400 gig ZR spec that's being developed for 80 kilometers. There, we would need some kind of dispersion compensation in the DSP in the receiver. But for most of these 2 kilometer links and below, that's not a consideration. Okay, so in the interest of time, I will skip over the next 2 slides, which essentially talk about commonly used FEC in these optical links in order to get the beta rate improvement, and DFE pre-coding method in order to limit the error propagation problem here. But there are references that delve into this in more detail if you're interested. So let's move to link budgeting. So like I mentioned, the problem here is the standards specify the sort of end-to-end data rate, bandwidth, and bit rate target, and so you know what kind of SNR you need to meet. But you have to figure out, okay, how do you divvy up that on the electrical side between, say, insertion loss, both in this case from the chip to module scenario, insertion loss from the host to the connector, the module to the connector, and so forth, and the crosstalk between those channels. And on the optical side, you have a certain budget, and so you have to figure out, okay, how do I allocate it between the channel loss, the modulation loss, all the other loss mechanisms, given a certain receiver sensitivity. So the method used is a little different on the electrical and optical side. The optical side is relatively more straightforward, so I'll focus on the electrical side, which where people have converged around this methodology called the channel operating margin, or COM, which has actually been adopted by IEEE as kind of a standardized way to budget these links, and it's used extensively in the standards development process. So let's look a little bit more into what COM is. It's basically a way to tie sort of your SerDes and channel specs into one, rather than specifying them piecemeal. So it used to be that the standards would say, okay, the transmitter needs to meet this mask, the channel needs to meet this mask, the receiver should work with this input mask. But that quickly became sort of unworkable at these higher signaling rates and with PAM4 modulation, given the significant interactions between all these components. So COM was sort of proposed and adopted as a way to sort of tie all these together. And like I mentioned, it's very commonly used in the standards development process to evaluate sort of competing proposals COM is used as a sort of a way to choose one over the other or figure out what the solution space is for a particular proposal. So it's essentially nothing but signal to noise ratio metric. So it's just the ratio of your average signal to the total noise, and I mean noise including both systematic and random components for a certain target bit error rate. So most of the subtleties are in this reference model and what model is used to derive this I. So that's where people have now converged on what's the useful reference model, what are the parameters for the reference model, and so forth. But once you have that, it's relatively straightforward to compute what your channel operating margin is. The number to remember is 3 dB. Most standards, I mean, they've agreed that greater than 3 dB of COM is equivalent, I mean, is sufficient margin in order to achieve or close the link. So this means that your signal needs to be like 40%, at least 40% higher than your overall noise. So the reference model itself that's used for the channel operating margin computation, it essentially converts this physical topology that you have into this more abstract analytical model, which includes models for all the SerDes components, at least all the relevant SerDes components for signaling analysis, like the TX-FFE, and on the receive side, the CTLE and DFE, and models for all the components of the intermediate channel. So in addition to the main channel, like I mentioned, the package is usually a significant limiter in these links. So there are models for the package as well. And all these models are parameterized, and the standards define what parameters to use for these models so that people can use them and get consistent results. So the computation of COM, once you have the reference model, the computation of COM itself is kind of a 3-step process. The first step is computing what's called the single bit response, which is essentially what's the response you see on the receiver if you send a single pulse, one UI pulse on the transmit side. And here we're assuming that the overall chain is linear, so you can get the overall response by essentially multiplying the frequency response from your TX-FFE, your channel, your receive filter, and your continuous time linear equalizer. And again, as you can see here, these are parameterized, and there are systematic ways to compute them to get consistent results. The trickier part is the second step, which is the equalization search. So here the problem is to determine what is your optimal equalization settings for transmitter FFE, your receive CTLE, and your DFE. And there's actually a pretty hard problem to solve exactly, so people resort to approximations. The agreed upon approximation here is, okay, rather than optimizing, finding the equalization settings to get the best bit error rate, we'll optimize a simpler form instead. So the figure of merit is this sort of SNR definition where all the noise and interference sources are assumed to be these uncorrelated Gaussian distributions, and so you sum up their standard deviations from your whatever impairments your TX has, your channel, the jitter, and crosstalk, and so forth. And we go through a search process in this equalization space in order to get the best form. Again, there's references that describe this in more detail. But once you've figured that out, then the step 3, you use that to derive a more exact distribution of the noise profile on your signal. And this is important because the COM computation itself relies on a ratio of the signal to noise. So for this step, you actually do a better job of trying to get that noise profile without making the simplifying approximations in the equalization optimization. So here we take into account the deterministic nature of ISI and crosstalk, deterministic and bounded nature of ISI and crosstalk. and then convolve it with all the other sort of more Gaussian noise sources to get a more accurate representation of your receiver noise distribution, and then finally use that in order to do your computation. So here's an sort of example result from going through this exercise. So the different bathtub curves, if you start from the right here, the first curve is if you didn't have any additional noise. So that gives you what your signal amplitude is. So this includes only just ISI. And then you progressively add crosstalk, jitter, and sort of other noise sources to end up with this black curve here. And you look at your target bit rate, what's the difference between these two. That gives the noise that's added to the signal. And then you simply take the ratio of these two, convert it to dB, and compare it to that 3 dB target that we have. And so in this case, we actually meet that target. So this is the kind of analysis that people do for all when trying to evaluate, going through these channel budgeting exercises like what's shown here. So here, if you want to evaluate what our performance is going to be over 5 different channels, which have different insertion loss profiles, but have sort of with similar crosstalk characteristics. We want to see, okay, for a given sort of SerDes configuration, which, if any of these channels will meet your target. So you can go through the COM exercise like we showed before, and figure out, okay, in this case, that actually adding crosstalk completely sort of makes all of them fail by a significant amount. And so clearly this indicates that you either need to significantly reduce your ICN or integrated crosstalk noise, or improve your actual SerDes equalization capability. So typically, most 56 gig link designs target much lower values of ICN, like 2 millivolts or below. So this is clearly an indication that the crosstalk is way above spec. And people use similar analysis for, like I mentioned, when talking about going through the standards process. So here's an example from a 112 gig standards presentation from Intel, where people are looking at, okay, what kind of equalization is required in order to close the link budget at these rates for a given set of test channels that people have agreed upon. And here, the exercise is to see, okay, with increasing FFE tap complexity, what benefits do you get in order to identify, okay, what are the combinations of channel and FFE that actually help you meet the COM budget. So this is kind of to give you a flavor of the type of things that people do on a sort of routine basis in order during the standardization process to get an idea of the complexity, SerDes complexity for a given channel to meet the desired bandwidth targets. The optical link budget side is relatively more straightforward, and it's more of a spreadsheet type analysis where there are loss budgets for different components in the signal chain, and you add them up either to figure out what your transmit optical power needs to be, or for a given transmit optical power, what your receiver sensitivity needs to be. And so that's compared to the COM analysis on the electrical side, it's relatively more straightforward. And depending on the complexity of the link, whether it is wavelength division multiplexing or so forth, the number of components may be different, but the method itself remains the same. Okay, so let me go with the last section, which is the link modeling and analysis. And so here, the idea is to develop a model with an abstract model with enough details or just enough details to figure out what kind of link architectures are viable in order to meet the specifications of your standard and the budget that you've derived. So typical things that people study are the equalization architectures, how to divvy it up between the transmitter and the receiver, and between different forms of equalization, continuous time versus discrete time, linear versus DFE, and so forth. And similar analysis on the clocking side as well, to figure out how to break your jitter budget between different clocking elements. So in the interest of time, I'll focus primarily on, there are a bunch of methods that people have proposed over the years for link modeling, but the one that's used by and large, or some form of it is used by and large now for these higher speed links, is this time domain based simulations, primarily because the relaxation of the beta rate target makes this method a lot more practical than it used to be. And it can accommodate a lot of the impairments that actually have a demonstrable impact for PAM4, like nonlinearity, quantization effects, and so forth. So I'll mainly focus on this one, but there are references on the other techniques as well. So for electrical links, essentially the modeling is in three parts. So we have a model for the transmit side, we have a model for the receive side, and then we have a model for the channel, where the key thing to remember is to include the effects of crosstalk, which are far from negligible at these rates and with PAM4. And the crosstalk channels typically are assumed to have a small frequency offset from the main channel so that they're asynchronous with respect to the main channel. So on the TX side, we convert sort of this. What's shown on the top is sort of an actual 112 gig TX architecture, what it would look like, but we abstract it into sort of a simpler model that still includes the key elements of the TX, like a feed-forward equalizer, the finite resolution of the DAC, the jitter in your clocking, the nonlinearity compression that you typically see in your output stage, and your output voltage noise. And of course, the pad network, like I talked about, which is required to meet your return loss spec. And one important thing that's becoming more critical to model is your clock distribution. So here, because your clocks now span over a wider frequency range, there's significant random jitter being added in your clock distribution path, which can be captured using this jitter transfer function methodology that I'll probably not have time to go over today, but that's included in the reference. But that's something that's important to comprehend. Okay, so let me skip over this one. And then the receive side, again, it's kind of a similar abstraction method. We abstract all the linear filters into these frequency domain representations, and the other components in the more like behavioral time domain fashion, like the ADC, FFE, and so forth, and use a similar method to convert jitter from the time domain to voltage domain. So again, similar to the COM calculation, the equalizer optimization is a tricky thing here. Partly, even without the constraint of not having a back channel, the problem is actually pretty hard to figure out what's the optimal combination of transmit and receive side equalization in a general equalization scenario. So the approach people use is you kind of break it down into in two fashions. One is kind of sequence the search, and the other one is to use simplified figures of merit instead of the actual beta rate target. And a good simplification for the figure of merit is what is proposed in the COM, where you assume that the noise and interference is independent Gaussian distributions and add them together. And another common simplification that's used is to, rather than optimizing your overall beta rate, you optimize your mean square error, because for those you can get analytical solutions pretty quickly. Okay, so let's look at maybe couple of examples to see how these models are actually used in a real link design. So I think I have 3 examples. I'll go over one on the optical side and one on the electrical side to finish up the rest of the presentation. So on the electrical side, here the problem is, okay, so we have these 6 target channels that we want to signal over in order to meet some data rate and bit rate targets. And we want to choose between sort of different analog front-end options. Depending on what our CTLE is, whether it's a simple 102-pole type CTLE, whether it's a higher order system, and whether we need some kind of a post-CTLE filter in order to restrict the high-frequency noise. So 6 channels, 6 AFE options, and we want to figure out which among these 6 AFE options gives us the best performance over these 6 channels. So by using the models that I showed earlier and sort of plugging in the parameters for all the remaining things that I'm not showing here, we can easily generate data like what's shown here, where we can plot, okay, what's my eye height at target bit rate for these 6 channels, and for each channel, these 6 AFE options. And looking at this data can give us some insight into the design. For example, we can see by there's a consistent trend that we get a significant benefit by adding this sort of post-CTLE filter. And we also get a significant benefit by going from a 102-pole filter to a 204-pole filter consistently across most of the channels. So this is the kind of analysis that the models can enable in order to guide the design of an actual SerDes. And similarly, as pretty much all the SerDes designs are moving to an ADC DSP type architecture on the receiver, and then DSP and DAC architecture on the transmitter, we want to figure out, okay, what kind of resolutions do we need to support, and precisions do we need to support on these 2 sides. So we could do some analysis using the behavioral models earlier to get data that shows, okay, how does my voltage margin vary, in this case as a function of DSP resolution for a certain equalization architecture, to figure out, okay, what's the minimum resolution that I need in order to not have my performance be limited by my DSP resolution. And also, how do I distribute, so if I have a certain number of taps that I want to allocate, how do I distribute it between precursor taps and post-cursor taps and so forth. Okay. So let me skip over these examples. I mean, they're fairly self-explanatory, so you can read them from the slides. I'll skip over the clocking section, which is, there's actually a very good reference, there's reference 25 that I've listed that essentially details the clocking analysis methodology and how you can abstract the properties of the clock distribution network to a jitter transfer function that will help you analyze what your clocking solution needs to be. So I'll skip over this section and move to the optical link model. Okay, so here, this is kind of a typical abstraction of an optical link. So in these pluggable optical modules, there's typically a retimer, which is kind of a light SerDes. And the optical transceivers themselves, the driver and the TIA, are, for most part today, are discrete chips. So there is, even in an optical link, there's usually a short electrical link between the retimer and the driver, which is important to include in the overall model. But besides that, the key new models are the modulator and the photodiode. So I'll not go too much into the modulator modeling because I think the subsequent talk by Professor Azita will talk about that. But from a modeling standpoint, the key parameters here are obviously the bandwidth of the modulator, the linearity, which it's usually a matter of how much nonlinearity can you tolerate with optical modulators, and then the noise that they introduce. And like we saw before, all these three have a strong impact on that, on the TDECQ metric. But they may, I mean, there could be different, the standards allow different trade-offs to be made between these parameters. And with some equalization capability in the reference receiver, it's usually more important to constrain the nonlinearity and the noise than it is to extend the bandwidth of these modulators. So let me skip over the VCSEL model. Again, this is detailed in reference here. So I'll talk more about the PD model and an example on how we can use this model to do an optical receiver design. So the photodetector model typically has two components. One is just the photocurrent generator, which has a first order response that's limited by the transit time bandwidth of the PD, and then an electrical model that has the electrical interface between the PD and the pad, the output of the PD, which captures the key parameters here, the parasitic resistance and the PD cap. And I've listed some typical values for these, for most sort of high-speed optical transceiver designs, receiver designs. So the example I want to highlight here for the use of optical modeling is the design of this 56 gigabaud optical receiver. This is an exercise that we went through recently. So we have some characteristics for say a discrete PD in the form that I showed earlier. And the problem is now I want to design this receiver, which includes a TIA and potentially some post-TIA equalization. And I want to figure out, okay, what's the optimal parameters for these circuits in order to optimize my overall receiver sensitivity. So I want to be able to detect the minimum input power with this combination. So at a high level, the idea is to co-optimize these. The reason we can expect an optimal solution here is reduction in usually the main limitation is the TIA noise, the input referred noise. So we can reduce that by reducing the bandwidth of the TIA, but by doing that, we actually add more ISI, which we want to compensate without amplifying any of that ISI using this DFE. And so that's an approach that people are looking more and more at in order to optimize your overall receiver sensitivity, primarily in the context of sort of integrated CMOS optical receivers. So to do this, we can start with sort of simple analytical model of the shunt feedback TIA. And for a given technology, you can show that really the key parameters are the GM of this input stage and your feedback resistor. And in the case of more complicated TIAs, we could actually start with some step response or some kind of a frequency domain description of like a higher order TIA. But in either case, we can plug that model into a model for sort of the overall optical receiver and figure out, okay, for a given combination of these parameters, what's my pulse response, a single bit response, similar to what you do in a COM calculation. And you can fold in the effects of your CDR sampling point, your DFE, and so forth. And basically convert this entire signal chain into a single pulse response. And then convolve that with your PIBS waveform and figure out, okay, what's my beta rate for a given input signal level. And then you can do this exercise for different choice of these combinations of parameters, receiver parameters, and get plots like this that allow you to identify for sort of a given DFE scenario and PD capacitance, what's my optimum value of like GM and R feedback of my TIA. And eventually sort of summarize your results in plots like this that show the dependence of sensitivity, which is our final parameter of interest, as a function of, let's say, PD capacitance and different equalization scenarios to figure out, okay, how much benefit am I getting for the power and area and design complexity of a DFE. And so here I'm showing results for PAM2 and PAM4, showing that in both cases, at least in this example, a one-tap DFE does give you significant benefit, meaning the bandwidth reduction is actually a reasonable price to pay for the noise improvement you get from a DFE. But I mean, basically the idea is to, rather than focusing on the actual results, to illustrate what the models enable and how they guide sort of the circuit design decisions. Okay, so finally, so to conclude, we saw that there are basically two key standards that we have to pay attention to in the design of these 50 gig and higher electrical and optical links. From on the electrical side, typically the CEI standards, and on the optical side, the IEEE 802.3 standards. And in both of these are sort of under active development for the 112 gig regime. But there are no sort of dramatic changes like from 56 gig to 112 gig, like what we saw from 28 to 56 that are in the works. And then for link budgeting, we looked at the channel operating margin and saw how that can give you a standardized way to determine what your link budget needs to be for an electrical link. And then finally, we looked at some link modeling and examples on how they can enable sort of SerDes architecture exploration and validation. So finally, I want to acknowledge the help I got from the folks listed here in pulling the material for this presentation together. And there's also some references following this for if you're interested in looking at or delving into more details over any of the material that was presented here. So thank you.
Questions? Slide 52.
Oh, okay.
Is it that one-time DFE is desirable or is it just some arbitrary choice?
It's yeah, I'd say neither. The one-time, yeah. So okay. So the question was: is the one-time DFE desirable or is it an arbitrary choice? I mean, a DFE is desirable. It's possible to argue that more than multi-tap DFE is desirable. The one-tap limitation typically comes from just implementation considerations. It's usually more expensive to design multi-tap DFEs, and so that's why most of the analysis so far has been restricted to, okay, let's say we can do only a one-tap DFE, because there's no argument about the benefit you get with a DFE, and usually the maximum benefit comes from the first tap. And there's some incremental benefit beyond, but if it's not absolutely necessary and if you can do something similar by increasing the FFE complexity, that's what the preference has been so far. So that's primarily why, yeah, the restriction is with the one-tap DFE. But I mean, I think most likely you'll get more benefits with multi-tap DFE. The other consideration here is the error propagation issue. It's somewhat more straightforward to predict the error propagation behavior with the one-tap DFE. It becomes much more complicated with multi-tap. So that's.
So these the FFE tabs listed here, they are ideal, right? Without regard for what the size of the tabs are.
I think there is some. No, there are. In this case, there are considerations on what the precision of those tabs are. Meaning like how many bits are used to represent them and how precise they can be. So they're not floating point. But yeah, sorry. The question was: are the FFE tabs ideal, or is there any other limitation? I mean, there are some quantization limits that are applied on the FFE tabs themselves, but they are not. they're not the ones that are limiting the tap benefit. I think the bigger limit comes from the ADC resolution and the DAC resolution.
Just one more question. What is the filter used after the CTLE?
Oh, so that's a simple, in this analysis, it was just, so the question was, what's the filter used after the CTLE that gives benefits? In this, it's basically a simple fourth order, I believe it was a Bessel-Thomson filter. So if we go to, yeah, so the filter used here, the post-CTLA filter referred to here, it's an ideal fourth order Bessel-Thomson filter with bandwidth. I think in this case there was about 3/4 of the baud rate. So all this is doing is, it's filtering out. There's only so much noise filtering you're getting with the CTLE, and this one cuts off the frequency a little more. And for most part, it comes for free from the multi-stage VGA that follows it. But this was just to see, okay, how important is that?
I'll ask you one. So you mentioned that the crosstalk is much more detrimental for PAM4 at high speeds. The amount of crosstalk noise.
That's right. Right.
What are link designers doing to reduce the noise?
Yeah. So primarily, those design modifications to reduce crosstalk, they're primarily channel modifications. And there isn't anything that I'm aware of from a circuit side. I mean, people are not looking at active crosstalk cancellation, for example. Most of that, the reason for that is most of this crosstalk is coming, at least in the LR case, from the connectors, the backplane. So there are things you can do in the connectors, and also, okay, on the SerDes side itself, the one thing that people are paying much more attention to is how they break out these signals from the boards in order to minimize the crosstalk, the IC and the package itself. And we are outside that, it's in the connector, and modifications in that connector to minimize the crosstalk. So the approach has mostly been to control, look at ways to control crosstalk rather than accommodate it and cancel it.
I'll ask you. So when we were in the transceiver speed limited regime and the channel bandwidth was high enough, we kept on using NRZ, and with Moore's law, the speed kept on increasing. So if we hit that, then the channel, if bandwidth is not good enough, then there was a lot of work on making the channel wider bandwidth and things like that.
Right.
So which regime are we now? Are we receiver speed limited? That's why we are going to 4PAN? Or is it the bandwidth limitations are coming from the channel itself?
Yeah.
And on that note, the next 2x is going to come from where?
Right. So for the first question, I'd say the transition to 4PAM was PAM4 was primarily driven by the channel bandwidth limitations. In many of the backplane channels, there is pretty steep frequency roll-off going from 14 gigahertz to 28 gigahertz. But those are not present in the very short channels, which is why NRZ is still applicable there. So the technology itself allowed us to push the baud rate from 28 to 56. So the next one, it's a little more murky, from 56 gigabaud to, if you want, looking at 224 gigabits per second. If you want to stick with PAM4, then that would require 100 gigabaud circuits. I mean, that's an option that is still on the table. I think it's too early to say that that's not doable. The question more is is it doable at a reasonable power cost? So that's not clear. So that's why there are alternative modulation schemes on the table. Like people are looking at PAM4, which is not sufficient to give us the 2x, but it gets us partway there, and then an increase in baud rate. People are also looking at QAM 32 type higher order constellations in order to limit the baud rate. So I'd say that's still open. But when I said 224 is doable on the path, at least the path is, there are no significant showstoppers for that. But the actual, nobody has actually converged on the baud rate modulation scheme for that. There is a high probability that, that the modulation scheme could change to 24.
When you say there's no significant showstoppers for 224, have you looked at the Schematic capacity for now?
Yeah, so there, I mean, I haven't looked at it personally, but people have looked at what's the, so again, I should probably qualify it a little bit more. Most of the work so far has been looking not necessarily at the long reach type channels. A lot of the exploratory work has been in like the VSR channels or below. So the focus has primarily been on addressing the first part of Shreya's question, which was can we build circuits and modulation at least. So that it's typically how the standards evolve. People first want to solve the easier channel problem, and then, but from a channel capacity standpoint, at least the numbers I've seen in earlier presentations show that we are not near those capacity limits at 200K, even for existing LRs. No, for the LR with the, I would say like the cabled backplane type channel scenario for.
You mentioned BOM in one of your responses. So when would, for data center application, when would coherent detection become more cost-effective compared to this
Right. So I think there are scenarios in the data center where it's already, I mean, people are actively looking at that, and there is a strong case to be made that it, I mean, I think I would say that case has been made, and that's why the 400 gig ZR standard is already like well underway. But primarily, at least now, it's being targeted more for intra data center links, so like the 80 kilometer, tens of kilometers reach. So there, the value proposition is very, very clear. The difference from sort of the metro links is the power and cost considerations are much different, and so that's why we need a new standard. So there, I think we'll see it. In fact, the ICC, there were papers on coherent optical transceivers. So I think we'll see that very soon. There's also, at OFC, there were presentations from Facebook and Google on looking at coherent optics for shorter reach, like within 10 kilometer links, basically with very light ADC and DSP. So that's also gaining a lot of traction. So yeah, so we'll see that more and more. Although there'll still be some fragmentation between the intensity modulated links for at least up to 500 meters, and maybe beyond 2 kilometers, once we start seeing more proof of concepts coming out for coherent transceivers, we'll see more of that, more of coherent optics.
Any other questions? Okay, I'll ask you a last question.
Yeah.
I noticed you mentioned in one of your slides that almost all of the receivers for PAM4 are ADC and DSP based.
Almost.
Most of them. And I guess we have two speakers in our session today. One of them is going to be championing ADC and DSP based links, and the other one talking about base signal based links. So the base signal based links so far are lower power, have lower latency. Why is there so much excitement about ADC DSP?
Well, I'm sure. Yeah.
All right. So on that note, we'll conclude. And in order to get the answer for that question, I request you to come back and listen to your talk. Thank you.